The Week in the Life sessions follow Daniel, a typical corporate developer, through a week of writing code and improving existing solutions. As a corporate developer, Daniel has already been assigned to a development team for the BizLogic Corporation. The development team that Daniel has been assigned to is responsible for the maintenance of an in-house CRM application. The CRM application supports users on the local network, as well as remote users outside of the firewall. Because Daniel has excellent exposure to new technologies and their benefits, he was added to the team to improve application performance, stability, and availability for BizLogic CRM. Day 1 focused on back-end solutions, including how to best take advantage of existing hardware resources to increase agility and decrease costs, while continuing to ensure reliability and performance. Day 2 covered best practice enhancements for the middleware tier. This included using the Intel C++ compiler, improving threading, and recompiling for use on 64-bit hardware. The third day focused on client-side optimizations. Daniel created a performant client application to maximize user interface responsiveness and minimize any perceived sluggishness. Today focuses on the need for mobility in the client application. The main focus will be on recognizing the need for such things as power and network awareness, ensuring that Daniel's application provides mobile functionality, and ensuring that everything remains performant. The final day will focus on bringing the client application to the handheld device form factor. Daniel is aware of the increasing number of BizLogic employees that use notebook computers to run the CRM client while away from the office. To improve their experience with the application, he wants to add new features to make the client application network and power aware. The enhanced CRM client is able to work through network connections and disconnections, keeping the users productive through changing network conditions. Also, the CRM client needs to be able to be aware of low power situations and respond in a way to allow the user to conserve power. To begin with, we'll start with a discussion of the mobile market as it exists today. This should make it clear why mobile-enabled applications must no longer be considered a niche or enhanced feature set. More and more computers are being sold mobile-enabled than ever before. Between 2005 and 2009, notebook and tablet computer sales are projected to grow 14%, compared to only 3% growth for desktop computers. The addition of a growing number of budget-priced laptop models serves to encourage more users to buy a mobile computer than one tethered to a desk. BizLogic issues laptops for a large portion of their workforce, so their needs are as important as desktop users. As this trend continues, it becomes imperative that applications become mobility aware. What does that mean? Applications such as Internet Explorer and Microsoft Outlook demonstrate a powerful compromise of features in order to accommodate users with or without a network connection. File transfer applications often throttle transfer speeds based on available bandwidth. Applications that don't perform well on a mobile computer will begin to lose market share to those who do. Rather than resorting to a combination of Win32 calls, WMI events, and other sources, the Intel Mobile Platform SDK provides Windows developers with a unified interface into a wealth of system information related to mobility. An application can discover the presence and status of batteries, network adapters, display adapters, processors, and other devices. Determine what capabilities are supported in order to offer appropriate options to users or to fine-tune performance programmability. Remain aware of changes to states such as available bandwidth or network availability, even settling thresholds for notification. Using the information available from the Intel Mobile Platform SDK, you have the ability to modify your application's behavior based on real-time system state. For example, processor-intensive applications such as games could benefit from automatically scaling the level of detail up and down based on the power source or battery level. Automatic file saving can take place prior to system suspend, and network connections can seamlessly suspend and resume with network connectivity. Notebook computers were, until recently, considered exclusively high-priced luxury items. At the same time, it was understood that a notebook would always be underpowered compared to a cheaper desktop computer. While notebooks and tablets are still often more expensive than a comparable desktop, the performance gap is closing along with the price. The enterprise has historically been the strongest market for portable computers. The busy executive wanting to remain productive at all times has preferred a computer to be as mobile as he or she is. Industries such as healthcare have also seen a great benefit to providing their workers, especially physicians, with mobile computers that can be carried throughout the day. This provides the benefits of a user-specific computer, along with the required freedom from an office. Gradually, notebooks have also proved their worth for remote workers who seldom spend time in the office. As salesperson able to enter orders, view product information, and even display demonstrations from the computer, they can be much more effective. Similarly, an insurance claim worker can carry forms, pictures, and databases of claims and insured members in one place. More recently, the market for non-business laptops has really taken off. Students prefer a personal computer that can be used in class to take notes, around campus for collaboration, and in their dorm room for homework without worrying about keeping files in sync. With the advent of the budget laptop, people are increasingly looking to non-desktop computers as a primary home computer. The reduced desk space, along with the ability to take it on the road when necessary, makes them attractive options. For software developers wanting to reach the widest audience, it is imperative that certain assumptions are not made about the system environment. A desktop computer is generally considered to be predictable and consistent. In general, watching for user log-off and shutdown events is sufficient for an adaptable application. A desktop computer is expected to have a consistent network connection. This means that the connection remains online, with the same IP address, and with the same bandwidth available over time. Power is also considered a given. Many desktops are seldom shut down except in response to crashes or system updates. Applications can perform CPU-intensive operations without concern that processor speed may rise and fall due to power management throttling. Finally, the lack of battery power means that a desktop need not worry about low power and the risk of emergency shutdown. It is important to evaluate an application to determine how mobility might impact it. Failure to perform this evaluation could result in reduced market share, or in BizLogic's case, reduced output from their workforce. As more and more users adopt notebooks or tablets, expectations will rise that applications will adapt appropriately. Applications that do not will have a poor perception, especially compared to competing software that is mobile aware. This will result in lost sales and productivity. Most software currently is not aware of mobility factors, yet is run on notebooks and tablets anyway, out of necessity. This will often lead to poor performance, as power management profiles reduce overall performance in response to power events, yet applications do not adapt. Users will feel the reduction in application responsiveness and overall productivity and consider it a bad experience. This will create a new market for mobile-enabled alternatives. Applications have varying needs for mobility awareness. The most notable feature to which to add mobility support is networking. Connections being made and data being transferred is absent without a network connection, unlike battery issues which may just slow down the system. File transfers should be careful not to consume all available bandwidth. The ability to suspend and resume a transfer based on network availability is also a large part of a transparently mobile application. Graphics-intensive applications, such as games or modeling tools, tend to assume that graphics performance is the top priority. Though this is generally the case, if a system is set to maximize battery life, applications should automatically scale back graphics accordingly. Reducing the frame rate and/or the level of rendering detail can make a big difference for CPU utilization, which has a direct impact on battery life. CPU utilization can also be reduced by adapting algorithms based on available clock speed. For instance, a frequently called CPU-intensive function may be substituted by a less intensive and less precise implementation when demands warrant. Also keep in mind that as CPU throttling takes effect, the actual processor speed can change. Time-sensitive calculations may make an assumption of CPU speed based on application initialization. It is important to take into account that speed can change at any time. Now that you have seen some general information regarding mobile systems and how an application can function in a mobile-aware manner, we will discuss specific considerations that exist for mobility and how these are addressed with existing .NET features. In order to extract maximum performance from a mobile computer, considerations must be taken into account. Because power level is not a constant, strict attention must be given to the current state in order to adapt accordingly. The power source can change at any time. A notebook or tablet plugged into the wall will have the same steady source of power as a desktop. As soon as the plug is removed, however, several factors must be taken into account. The system may immediately switch to a power conservation mode. Depending on the current battery level, this conservation may be more or less severe. By regulating the operations performed by an application, the rate of battery drain can be affected. Users on battery power are generally willing to make trade-offs in performance in order to maximize battery life. CPU speed throttling using Intel SpeedStep technology occurs automatically based on current battery level. This behavior can be modified by the user by specifying different power policy schemes. Being aware of this selected policy can allow an application to scale performance in a manner in line with user expectations. Since the version 2.0 of the .NET framework, a number of mobility awareness features have been available to .NET developers. These reside in the system.win32 namespace. These are a large improvement over the previous Power APIs only available using the pinvoke facility for Win32 functions. The Power Mode Changed event is a static event to notify an application that the system has changed between power modes. When the event is fired, the application can determine the status via a three-state enumeration accessible through the mode property of the event object. If the mode is suspend, the system is about to be suspended. Note that this is a non-cancelable operation. Though APIs exist to reject a suspend request, they are unmanaged and are expected to be removed with Windows Vista. A system being suspended can save critical information to disk quickly and attempt to gracefully cease certain operation. An application typically has about 2 seconds to perform any actions. If the mode is resumed, the system has just been restored from a previous suspension. This can be useful for restoring state. Ideally, a user will not need to explicitly reinitiate operations when returning from suspend. The status change mode simply indicates that a power source change has occurred, either to battery or to AC. The power status object is in the system.information namespace and exposes fine-grained information about power similar to the power meter control panel applet. Properties such as whether the battery is currently charging, discharging, or full, the current percentage of battery capacity remaining, and the approximate remaining time are easy to use. Unlike the Intel Mobile Platform SDK, it is not possible to specifically enumerate multiple batteries, nor can the insertion or removal of batteries be detected. This sample demonstrates an event handler being added to detect power mode changes. The first step is to add an event handler to the static Power Mode Changed event. The method declaration for the event handler includes the Power Mode Changed event args object. This contains the mode property used to determine what action has taken place. The next step is to branch based on the mode property. This example responds to the status change event. Recall that this indicates that the system has switched between AC and battery. The final step is to instantiate a power status object and use it to determine an action to take. Here, the battery charge status is examined to see if the charge is low. This could also be used for an emergency save or other such response. An application should also take into account networking considerations to create the best experience. Various types of connections offer different trade-offs. A wireless network can result in frequent speed changes due to changes in signal strength and other environmental factors. Completely dropping and reconnecting is not an infrequent occurrence. Roaming between networks as a user moves about can cause not only network disconnects and reconnects, but also a complete network reconfiguration, including network, address, DNS and WIN servers, and maximum speed. A wired connection is typically the ideal connection, with most notebooks and tablets offering a 10, 100, or even 1000 megabit per second connection. This provides a high-speed, low-latency connection with a lower chance of changes. On the other hand, a notebook or tablet may switch from docked to non-docked state, rendering the wired connection unusable. Dial-up speed, though less common today, is still a concern. Dial-up speeds would necessitate only the most crucial data being transferred. For instance, perhaps commands would still be relayed, but non-critical data transfer would wait for a better connection. A connect-on-demand policy for a portable computer may also mean that transitioning to a connected state could take over a minute to complete, and depending on method of access, may incur per-minute charges. As with power management, the .NET framework also offers networking support. The System.NET namespace contains the Network Information class, with methods, properties, and static events to assist in determining network conditions. The network availability changed event is triggered whenever a machine transitions from a connected to a disconnected state. When the event is triggered, the Boolean isAvailable property of the network availability event args object provides an easy way to detect connection status. One thing to note, however, is that a network connection may be active, though the host of interest to the application may not be accessible. An additional step is to connect to or ping the host in question. For on-demand needs, the static getIsNetworkAvailable method of the network information object will provide the same information as the isAvailable property. Another static event of network information, network address changed, alerts an application that the address of a connected network adapter has changed. In order to retrieve adapter-specific information, the static getAllNetworkInterfaces method returns a collection of network interface objects. These can be used to read the adapter name, type, MAC address, and other intrinsic information, in addition to configuration information such as network addresses, DNS WIN servers, gateway, or protocol in use. As with the power sample, the first step is to subscribe to the event. In this case, network availability changed. The event handler includes an event data object, network availability event args. This contains the property isAvailable to determine if the connection is available or not with this event. The main purpose of this method is to determine the highest available speed based on all network adapters that are operating. Enumerate through all interfaces using getAllNetworkInterfaces, then examine the operational status property. For each adapter with a status of up, compare the speed property to the current highest value. Finally, using the speed information, the application can make a decision or perform an action. In this case, if the speed available is greater than a preset threshold, a save to network should occur. Adding mobility awareness may seem complicated. Fortunately, Daniel can leverage the Mobile Platform SDK by Intel to expose mobility-related information in a common interface. He can use this to simplify the process of mobilizing his applications for the best performance and user experience. The .NET Framework provides a variety of ways to adapt to changing power and network conditions, however, without a unified interface. Learning how to access mobility information requires discovering and learning a variety of objects in different namespaces. In contrast, the Intel Mobile Platform SDK provides a common set of functionality in an easily discoverable layout. The mobile SDK supports cross-platform usage across desktops, notebooks and tablets, and PDAs as appropriate. A high level of granularity allows an application to enumerate devices, be notified of additions and removals, and to be notified of property changes. Multiple batteries, network adapters, display adapters, and even processors can be queried independently, in addition to properties and capabilities common to the class of devices. The mobile SDK supports notification for changes in power source, network connectivity, and bandwidth, as with the base .NET classes, in addition to many more properties. Properties such as battery level can even raise alerts based on thresholds being met. Using the Intel Mobile SDK makes it a lot easier to adapt to mobility features such as connectivity coming and going, bandwidth changing, and power levels changing. You can also use it to query for information on your processors, memory, hard drive space, display information. It's got a wealth of information about your system, and it enables you to subscribe to changes in many of those properties, and to even set thresholds to only be notified when properties change a certain amount. This is the Intel CRM application in design mode. In the bottom right-hand corner, in the status area, we have regions set aside to show connectivity, network bandwidth amount, current power source, and battery level. Let's take a look at the code. The intel.mobile.base, .context, and .threshold provide the functionality that we need. The context class is where it all begins. It's from the context class that you're able to get various capabilities of the system, which include your connectivity, your bandwidth, and your power. Here we've declared a threshold and observers. Observers are similar to delegates in .NET in that they allow you to register a function to be invoked by another function. And they're used in the case of events and thresholds so that when a certain change occurs, we're notified, and the means by which we're notified is by the event that we pass, the observer, being invoked. So we've created our new context class, and now from that context, we're going to get an instance for connectivity, and for bandwidth, and for power. Then we're creating a change observer. Now the Intel SDK defines the observer object. For easier .NET integration, this sample uses the delegate observer class, which is defined here. And the delegate observer makes it easier to use the .NET pattern of delegates instead of having to use observer as a base class and defining a whole new class. Then you choose a property, in this case status changed. Say you want to add an observer and pass that observer object, in our case the delegate observer, to be invoked when the status changed property changes. Similarly, we create a different delegate observer for bandwidth changes, and we register it to be invoked based on the status changed property changing, or for power, based on the source or the capacity changing. We also create a threshold so that if the battery falls below 95% or over 98%, we want to be notified of this. So we set which property we're watching, and then observer to be invoked, and then we start it, and it will check the value every, in this case, 1 second, every 1,000 milliseconds. And then the application starts up by invoking the event handlers without an event, just to force them to update and to make changes to the display. The connectivity event handler, after making sure that it's running on the UI thread, it checks to see the value of the isConnected property. But then instead of just saying that it's online because it's connected, it takes an extra step of connecting to, in this case, Intel.com. For a production application, you'd probably want it to be connecting to your domain server, your database server, your middleware server, something that's relevant to the application to indicate that not only do I have a connection to the network, but that I'm able to reach the host that I'm interested in. So assuming it can, it states online in that status bar. Otherwise, it states that it's online, but it can't reach the host. Finally, if it can't do anything, if it's not connected to a network, then it states that it's offline. For the bandwidth event handler, if we're online when this is invoked, it checks to see if there are any limits on receive or transmit. And then it either obtains the value of the limit or the actual system rate. We may have an adapter with that gives us a system rate of 100 megabit per second, but we may have a bandwidth restriction in place giving us only 5 megabit per second. Then we convert that to a text display and set that to the status label. We use the dash if we're offline. For the power event handler, once again, we make sure that we're on the right thread. We check to see if our power source is internal or external. And then we set that to a string and put that into the user interface. Finally, our low power event handler is the one that's invoked from the threshold. And that checks to see if the percent remaining is either below the low threshold or higher than the high threshold. This is up to us to know what to do with it. So all of this has been defined in the threshold. We wouldn't have been invoked if it wasn't one of these events, but it's up to us now to determine which is it that happened. And then if the battery is too low based on that threshold, we set the background of the battery number to red. Otherwise, we set it to known_color.control, which is just the typical gray background that users are accustomed to seeing. Now we're ready to begin the application. And recall that even before any events fire, it will automatically call each of them with a null event so that it initializes the display. So this shows that we're currently online. We have 100 megabit per second upstream and downstream. We're on AC power and the battery's at 100%. If we disconnect the power, we'll show that it goes to battery level. We're still online, we have full bandwidth, but we're running on battery power. And it indicates that we have 99% battery level. So let's reconnect the power. And you can see we're now back on AC. You can also manage the bandwidth limits. And we've now adjusted how much up and down bandwidth this is allowed. Now we did not implement this by setting the value through that form that just popped up and then changing it down here. What's changing down here is based on the status changed property and the observer that we created for it. So that demonstrates that it made the change, it set it, and it actually did take effect. And in fact, if we run the context directory report, came up in a few seconds. If we set ourselves down low enough and run that same report again, we should see a distinct difference in the time it takes to run. So as you can see, it's very responsive to changes in mobility. If we were to disconnect the network connection, it would switch between online and offline. I can't do that in this presentation, but if you want to follow the lab yourself, when you get to this point, disconnect your network adapter, right-click disable it, remove it, whatever you need to do, take out your network cable, and you will see it respond pretty quickly to show that it's changing between online and offline, and then it can change its logic internally for how it's going to interact with the data store based on that status. The device layer exposes a common object model for the lower level components like the battery, network adapter, and processor. Querying properties of system devices and registering for change events occurs at this layer. The capability layer is also known as the context layer and allows an application to discover, manipulate, and interact with capabilities such as power or connectivity without respect to the actual devices supporting the capabilities. In other words, an application can determine aggregate system capabilities that may be determined by multiple properties of multiple applications. Changes to capabilities can be tracked using event notification. The mobility adaptation layer provides a policy component and an interaction component. Using a combination of user, application, and system-defined rules, changes can be made to create the best configuration based on conditions being met. The application awareness layer allows an application to be controlled by the policy system and to inform the other layers of expectations. The Intel Mobile Platform SDK has a great advantage in offering a consistent API across various language environments including .NET, Java, and C++. Though the underlying code is in C++, the Java and .NET wrappers are included for easy integration. Learning the object model and overall structure of the libraries for one language makes it easy to apply that knowledge to other languages. In addition to language consistency, the Mobile Platform SDK is also consistent across various hardware platforms, including various Pentium processors and systems utilizing the Centrino chipset. Whether developing for a notebook or tablet or even a non-mobile desktop computer, well-written code will operate seamlessly. This allows one application binary to be mobile aware on a portable computer, while adapting to the exact configuration of a non-mobile computer as well. The Mobile SDK can also be used on Windows Mobile Edition 2003 PDA devices, including smartphones, using the Personal Internet Client architecture. The primary purpose of the Intel Mobile SDK is to provide programmatic access to low-level information regarding devices and capabilities. Rather than just determine aggregate capabilities, as with the included .NET Framework 2.0 classes, it is possible to isolate information about batteries and processors to the specific instance level. It is possible to read information across the class of devices such as batteries in general, or processors in general. But by enumerating specific devices, it is possible to build a very granular profile about the operating environment. By querying for device capabilities, it is possible for an application to determine characteristics of the system, such as if a network interface is wired or wireless, whether Bluetooth is available, and properties of the processor or processors present. The object model of the Mobile SDK provides a common API for accessing platform features. This makes it easier to bridge the gap between software features and actual device capabilities. It is easy to both retrieve device information and to subscribe to events that indicate changes in the devices. For example, a battery transitioning to a fully charged state can raise an event for appropriate application reaction. A variety of devices are supported by the SDK, including batteries, network adapters, and processors. The API simplifies the learning curve, so interacting with one class of devices makes it trivial to work with another class of devices. Device instances, properties, and events are easily discoverable, allowing for a highly dynamic application. 7 device class and instance types are supported by the SDK. These are the battery, platform, processor, network adapter, link protocol, display adapter, and storage device. Further details are in the next 2 slides. The battery class provides access to information, policies, and events related to system batteries. APIs include estimated time remaining and life percentage remaining. 2 of its key events include fully charged to indicate the full charge state of a battery, and going offline to indicate that a battery is no longer powering the system. The network adapter class provides information regarding network adapters present in the system. The enabled property indicates if the device is enabled, while net connection status indicates states such as connecting, disconnecting, hardware disabled, and more. Adapters are also further divided into radio and wired. Link protocols specify OSI Layer 2 and Layer 3 properties, such as IP address for both IPv4 and IPv6, current receive and transmit data rate in bits per second. Events such as connection and disconnection are exposed with media connect and media disconnect respectively. The platform class exposes hardware-based information useful for the adaptation subsystem but not available in other classes. This includes transitions such as sleep, standby, and restore. Key API calls include requesting a shutdown or suspend using the request shutdown or request suspend methods respectively. A Boolean return value indicates if the request was successful. Corresponding events notify an application to events such as shutting down or suspending. The processor class indicates the current frequency of a given processor in megahertz. It is also possible to query for hyperthreading technology or streaming SIMD extensions or SSE support. The display adapter class makes available properties such as the horizontal and vertical resolution, in addition to brightness, refresh rate, and color depth. Many of these are modifiable. The storage device classes allow an application to determine amount of free space, a list of logical disks, and extended information such as the format and physical disk layout. The added and removed events make it possible to detect changes to the system storage devices. The adaptation subsystem of the Mobile Platform SDK utilizes 2 types of objects to work with system devices. Class objects represent class of instances. These expose information that pertains to a group of similar entities. Class objects expose methods to get a specific device instance or a collection of all instances. For example, from a battery class object it is possible to obtain 1 or more battery instance objects. Instance objects are the actual entities themselves. These objects provide properties, methods, and events for a specific interface. The code sample demonstrates obtaining the battery class object, then retrieving a specific battery instance. The ID for instance would need to be retrieved previously, most likely by iterating through a collection of instances or presenting a list to a user. Finally, the capacity of the battery is emitted to the console. Properties are data members of the instance objects themselves. Properties in the Mobile SDK are more than a simple value, they are classes themselves. Properties have characteristics to query in order to expose corresponding metadata. In addition to the actual value, an application can query the data type of the property, such as integer, string, or Boolean, using the getType method. Many properties can be set or null. For these properties, it is a good idea to check if the value is null prior to calling the getValue method. The isNull method returns true if the value is not actually set. Some properties are inherited from the device class. These are called static property values and they cannot be modified. Changeable properties can be modified after instantiation. Use the isStatic method to check for this. All properties are gettable, but some may be read-only. The isSettable method exposes if a value can be modified. A property's parent instant object can be retrieved using the getParent method. This can be used when events pass a property to code in an observer. Instance objects have the ability to do more than just return information on the devices. They can also monitor changing properties and raise appropriate events. Such events can be based on a simple change, or in some cases on defined thresholds. Such notification can occur in real time for changes, or based on specified time granularity for thresholds. By judicious use of change events, an application can modify its behavior for an optimal experience. Thresholds can be tied to most properties and allow an application to only focus on high-priority events. A threshold could be tied to battery level or available bandwidth. Both standard events and threshold-based events function by executing a specified callback routine. Events are supported by both class object types and instance object types. They are used to notify one object about a change in another. Most class objects support two events, added and removed. These are used to indicate the creation or destruction of a corresponding class object instance. Not all class object types support these events. For instance, a processor cannot be added or removed dynamically, so the events would make no sense. Instant objects types support a single event, status changed, which is available for all intrinsic properties. This allows the application to register for notification of changes to any property of an instance object. The actual callback for an event is handled using a user-defined class deriving from Observer. This provides a consistent experience between Java, C++, and .NET, instead of .NET native features like delegates. Thresholds are application-defined events to indicate that a defined transition has occurred. They do not work with static properties. Three types of thresholds are available. The counter threshold type can be used with integer and datetime properties. Gauge threshold works with integer, datetime, and float properties. Value threshold works with string properties. In order to create and work with a threshold, 4 general steps must be taken. First, an actual threshold object must be created. Second, the property of interest must be set using the setObservedProperty method. Next, the firing criteria is specified. Finally, an observer object is added to the threshold. Thresholds fire depending on the set condition and the current value of the property based on a configurable time granularity. This granularity can be as low as a second and is modified using the setGranularityPeriod method. In order to receive notification of events, an observer must be added to the event of interest. This class must implement the notify event. It is this event that is invoked when the event is fired. In order to associate an observer with an event, the addObserver method is called. For instance, each property object for a device's instance object type exposes an addObserver method. Similarly, application-created thresholds also support observers using this method. Using the observer pattern is not necessarily ideal in a .NET application. For one thing, as with Java, classes do not support multiple inheritance. This makes it impossible for a form or custom control to directly implement the notify method. One option is to create a secondary class to directly add as observer and to take actions based on events. Another option is to create an observer/delegate bridge class. This can be reused for all types of interest and allows any class, including one already deriving from a base class, to expose methods as event handlers. This fits well in the .NET paradigm. System capabilities provide a higher level of abstraction than devices. These expose system information at a functional level rather than a physical device level. The system capabilities include power, connectivity, bandwidth, storage, and display. Each capability has corresponding methods and/or properties. The power capability represents a system-wide view of all power sources. Properties include time remaining, which takes into account historic and statistical information, and actual current rate of power draw in milliwatts for the internal power source. Events can fire when the system switches between power sources or when the batteries are fully charged. The connectivity capability indicates networking and communication attributes. The isReachable method makes it easy to detect the ability to connect to a host. This is more useful in many cases than simply knowing that a network interface has a connection to a network, as the connected property shows. Events indicate a connection being established or dropped, or the network IP address being changed. The Intel Mobile SDK supports bandwidth policy control at the system, application, process, and socket levels. These are all accessible using the Bandwidth Policy Manager application. From within an application, bandwidth can be managed for the process itself and owned connections. Properties indicate the aggregated transmit and receive rates in kilobits per second across the system. The limit TX and limit RX properties indicate the allowed bandwidth for the current process. The bandwidth changed event can fire to indicate that system bandwidth changes, which can occur when the link speed of any connection changes. The storage capability encompasses memory, hard drives, and other storage devices. The persistent capacity indicates total capacity in kilobytes for all writable disks. The total physical memory property returns total memory, also in kilobytes. Finally, the display capability handles all attached display adapters, with the ability to aggregate information such as total display size across multiple monitors. Other properties include the color depth, described as the number of bits per pixel, the pixel density, expressed as dots per inch, and the orientation, which can be landscape or portrait, especially useful with a tablet device. The Mobile Platform SDK comes with several handy tools. The first is the Information Viewer. This application provides a powerful graphical user interface to access much of the functionality provided by the SDK. This allows you to view devices and capabilities in a unified tree view. You can see the various properties and events available on all of the objects and view current property values. You can register for simple event registration or create thresholds, and the application will log the event in the bottom pane when it fires. Another application provided with the SDK is the Mobile Bandwidth module. This application lets you set bandwidth limits system-wide, per process, or per socket or session. The tree view control shows all of the applications running and the communication sessions they have active. Clicking any item brings up a dialog box that allows you to set bandwidth limits. Both transfer and receive limits can be set at the same time with a Set Both Limits checkbox. Limits can be set to absolute rates or to a limit of available bandwidth. The graphic readout on the bottom has a real-time display of the current bandwidth utilization. So today Daniel has explored how mobile-enabled systems are slowly taking over, and it's no longer safe to assume that most users are running on a traditional desktop form factor, certainly something true of BizLogic employees. With the release of the .NET Framework 2.0, several new mobility features were added. While these help provide basic support for some applications, they still don't support details such as granular processor details or in-depth battery information. The Intel Mobile Platform SDK provides a common interface between C++, Java, and .NET, offering a wealth of information in a unified API. Learning the basic class structure makes it easy to leverage any of the included capabilities, devices, or properties. As you've seen today, network is never a given. Be it wireless networks or wired networks, local network or upstream providers, network connections cannot be expected to be steady. Especially with wireless networks, but also due to contention with other applications and networked computers, bandwidth cannot be assumed to be constant. Deal with this fluctuation by scaling data transfer as necessary without user intervention. AC power is a steady source, but as soon as the plug is pulled, trade-offs must be made to conserve the limited battery power. Scaling back CPU-intensive operations when necessary can maximize battery life and provide a better experience for your users. Always performing as though the network bandwidth and power won't change is a sure recipe for disaster. Sluggish response, decreased battery life, and contention with other applications will create a negative impression of your application. You cannot assume best case throughout your code. Respond to changes as appropriate for optimal performance. Using the Intel Mobile Platform SDK, your applications can provide the best performance based on currently available resources. For a small amount of effort, you can achieve great returns. For more information about the Intel Mobile Platform SDK, you can visit the homepage on the web.